First speaker is Professor Mercouri, the Kanatzidis. Please let me introduce him. The Professor, the Kanatzidis, is Charlie E. and Emma H., the Morrison Chair, Professor of Chemistry and Professor of Material Science and Engineering at Northwestern University, and Senior Scientist at Argonne, the National Lab. He is a 2022 the Global Energy Prize laureate. He has been listed as one of the most cited researchers in chemistry. He has received the Annie Award for the Renewable Energy Prize category and ACS Award in Inorganic Chemistry. He has mentored over 90 PhD students and nearly 120 postdoctoral fellows. With his team, he reported the first solid-state solar cell device using a film of the tin iodide perovskite in a solid-state dye-sensitized gradual cell with a 10% efficiency. He also discovered that perovskite materials currently implanted in the most efficient and stable the solar cell. Please welcome Professor Kanatzidis.
Thank you very much. Thank you very much for this kind introduction and for the invitation to speak in this really interesting symposium that covers so many aspects of cutting-edge science. Today, I would like to talk to you about our work on halide perovskites, which is a very, very hot topic from multiple perspectives, and let you tell you our story of this, how we got into it and what we have done, and some of the insights that we have developed over the years on how these things work. So first, I would like to acknowledge my group and collaborators. This is a snapshot of my group for last spring. I'm fortunate to have a great group of brilliant graduate students and postdocs and visitors from all over the world, and also brilliant collaborators, some of whom are shown here. This is not an all-inclusive, but I would like to highlight my great collaborator Aditya Mohida at Rice University, who is one of the most brilliant and creative scientists and engineers and makes great solar cells. Professor Jackie Yvain and Professor Claudine Catan, they are in France, University of Rennes, and they are the top, in my view, among the top theorists in the field of perovskites. Also, Ram Sesadri, the University of California, Santa Barbara, Alex Navrotsky, now she's actually the Arizona State University, Saiful Islam and Richard Schaller at Northwestern, and then some students who were involved in the work that I'm going to tell you about. That is Justin Hoffman, who is now a postdoc at Argonne National Lab, Dr. Yannis Panopoulos, who is now assistant professor at the University of South Florida, Eugenia Vasiliadou, who is now a postdoc at Caltech, Xiaotong Li, who is now a postdoc at Caltech, Jared Fletcher, who is a third-year graduate student, and Adam Balvans, who is now a second-year graduate student. So not everyone in my group is doing perovskites. Of course, we're interested in many things, and here's sort of an overview of what my research program is about. Essentially, we have the core activity is synthesis science, materials design and discovery. And then from there, it's like a nursery. We discover impactful compounds and materials that have influence in other areas. And so that's how we have discovered and made breakthroughs in thermoelectric materials conversion, in nonlinear optics. These are top performing materials in these areas, and they were all discovered from our synthesis science project. Materials for nuclear remediation, the organic perovskites, which I'm going to talk about today, and also another axis of perovskite research, which is X-ray and gamma ray detectors, which is a whole other talk, and I don't have time to actually cover that area. Okay, to perovskites. So what is a perovskite? This is, I understand, a general symposium, so some students may not be very familiar, although I'm sure most of them have already heard about the perovskites. These are these three-dimensional structures. As a structure type, it is known for over 100 years, but they occur in oxides, which are the better known materials, the oxide perovskites, and then the halides, which emerged as really revolutionary materials and semiconductors for solar cell devices, optoelectronic devices, and detectors. And this is this three-dimensional structure, an inorganic structure that is defined by octahedra of a metal that are joined at the corners. And so they share corners to develop this three-dimensional structure that you see here. In the case of halides, the most important perovskites are the lead halides and the tin halides. And they make this anionic framework. Lead is 2+ and tin is 2+. And this network makes cages, and because it's anionic, it needs to be charge balanced. And so it has an extra cation in the cages. And then only 3 cations fit in those cages: methylammonium, formamidinium, and cesium. If the cation is bigger, any bigger than that, then it doesn't fit in the cage and destabilizes the structure. It doesn't form. If it's too small than the cage, then it still destabilizes the structure. So it's only these 3 cations that readily go in there. So why are these materials so exciting? Well, a number of reasons, but reason number 1 is the fact that it's soluble in polar organic solvents. So you can make a solution of these materials, and then you can deposit the solution on the substrate and then recover a film that is the exact material that you started with and dissolve. So you can actually cast thin films readily in the lab by making solutions. No fancy equipment or expensive equipment required. So that's number 1. By itself is not enough, and I'll tell you the other reasons for it. But because you can process it at room temperature, you can make devices relatively easily, but also many people can be involved because the barrier to entry is very low. Any chemist, for example, can get involved in this field and start making films and devices. And now, I believe we have to give credit to Michael Gretzel for this field being what it is, because before the perovskites, there was another solar cell that we call the Gretzel cell, or dye-sensitized cell, that was announced in 1991. And that cell was also similar in the sense that many chemists could actually be involved, because to make the dye-sensitized cell was relatively easy, because it involved only chemical solution processing. And so Michael Gretzel made this cell, and it reached about 10% efficiency by 2011 around, and which was remarkable. The problem was that because it's a solution device, the device actually has solvent in it. It was not very stable, and it would decompose within months. And so no one was happy with this, and everybody was clamoring for a solid-state device that would solve the stability problem. And so our work was inspired by that, and therefore we wouldn't have done what we did if it wasn't for the Gretzel cell. So in saying that, we published this paper in May of 2012, reporting an all solid-state dye-sensitized cell based on the perovskite material. Now, we were working on perovskites in 2008, 9, 10, for a different reason. And in 2012, we got together, I got together with my collaborator, Bob Chang at Northwestern, who was working at Gressel cells. And he was trying to stabilize them and make them solid. And so I suggested to him, we use the perovskite as the replacement for the solvent because it could do the same job. It could actually transport the holes across the device. And that I suggested that because I knew a lot about this material from all the work we did the 3 years before that. So this is the device in the lower left of the Gressel device. It's very thick and it has acetonitrile. And the reason it has that is because it has to transfer the holes across the device. The electrons go on the other end after they're absorbed by the dye. And this process is a redox process. It's a redox chemistry of iodide, triiodide, and hepes in solution. In other words, we needed a p-type material that could be deposited from solution, and that's what we had with cesium tin iodide, and then demonstrated 10% efficiency in this thing, which took the entire community by surprise. Now, as the time went on, in September and in August of 2012, two more papers came out. One was from Korea, from Namgyu Park, with his student. The first author is Huison Kim. And they reported, and the second was from Henry Snaith and Tamotsu Miyazaka. These papers were submitted 2 weeks after our paper was published. And in fact, they cited our work in those papers. And they reported solar cells, solid-state solar cells, using another perovskite they had led, of 11% and 9%. And that also took the community by surprise. And then later, of course, others came in and reported the same cells with higher and higher efficiencies. And that started the whole field in 2012. Now, because of our work that we did the years prior to our publication, we had a lot of knowledge and a lot of experimental data about these perovskites, almost 20 compounds with different cations like methylammonium, formamidinium, cesium, and different halides, that we published this paper in Inorganic Chemistry that contained basically all the correct synthesis, reproducible synthesis, crystallographic data, coordinates, properties, property trends, and explanations of the property trends. And this paper came out right at the right time, where everybody was trying to figure out and find out information and understanding of these materials. So this came out in Inorganic Chemistry. It is the highest paper ever in the history of inorganic chemistry, which was established the journal was established in 1960, and it's the most read paper in that journal. So this paper, in fact, was rejected by another journal of the ACS because the referee said it lacked broad interest. Anyway, then we published this other paper in Nature Photonics on another tin-based perovskite solar cell in 2014. So these materials are incredible in the sense that they have an electronic structure, a band structure that you see on the right, that has very broad bands, and it's a direct band gap. And you see here, this is the Fermi level, this line, and we have this valence band, which is relatively broad, and we have a conduction band, which is also broad. And therefore, there's symmetry between the valence band and the conduction band. And you don't see that very often. Most of the times, you see a semiconductor that is not so interesting. It may have a good conduction band, but the valence band would be very flat. And that means that the holes are very heavy. And the electrons may be lighter. But here we have a balance in the effective mass for holes and electrons. And that characteristic is similar to gallium arsenide and 3,5 compounds and silicon and germanium and other things. And so it's closer to that electronically. And that's another reason why these materials are very good, do what they do. So the halide perovskites were known already for a long time before that. But no one cared until these 3 publications that came out in 2012. And then after that, you see these are publications on halide perovskites before 2012 and then after 2012. And it sort of skyrocketed since then. And then people demonstrated tremendous performance progress, as well as other devices, ultra-sensitive photodetectors, ultra-low threshold lasers, light-emitting diode, gamma and X-ray detectors, and now even catalysts and other things. So it's incredible what's going on. We never expected that actually this will happen back in 2012. So what are some of the remarkable properties of the halides, or the halide perovskites? One is the band gaps. They're direct, and they get bigger with rising temperature. Normally, a band gap of a semiconductor gets smaller with rising temperature because of thermal band broadening. These band gaps are opposite to what we know. They get bigger. I will explain why later. That makes them stable at high temperature. Both the conduction band and valence band are equally broad. I already talked about that. Similar hole and electron masses. No mid-gap states and very few traps that will trap the carriers. Very important. When you mix lead and tin, there's an anomalous band gap trend that is very useful to the device community. I will talk about that too. The lattice of the structure is very dynamic, and in fact disordered sometimes. In some ways it's disordered, and it's fluid-like. Seems to vibrate at all frequencies, and that is, I think, also important. This doesn't sound like a very good property, but actually it is. And that gives rise to rather long carrier lifetimes, elevated ionic dielectric responses, and defect tolerance. So, why are these things happening? And first of all, there's a clue in the fact that only lead and tin are the high-performing materials. If you replace them with other things like cadmium or strontium or other systems, they don't perform at all. And what they have in common, being 2+, they have the lone pair of electrons. These are group 4, so in principle, they can oxidize all the way to 4+. But here, they stop at 2+. And so they have an electron, a lone pair of electrons. And we know from the chemistry of water and ammonia, which are bent molecules, that the lone pair of electrons in oxygen, 2 of them, they want their own space, and they make the water molecule become bent. The nitrogen lone pair, it wants its own space, so it makes the ammonia molecule become bent. And so that is a fundamental property of the lone pair, and these atoms also have this property. And so, in fact, the entire group, germanium 2, tin 2, and lead 2+, they have the tendency to distort because of the lone pair becoming stereochemically expressed. And the tendency is greater as you get lighter in the group. So germanium has stronger tendency than tin, which is stronger than lead. That means that there is a natural thermodynamic tendency for the atom to go off-center in the octahedron, because the octahedron is totally symmetric and it doesn't allow any room for the lone pair. So these atoms are pushing to get off-centering, but the structure is pushing them back into the center of the octahedron. And so there is a big competition between these two effects. In fact, theory also predicts that when you move the atom away from the center and you calculate the energy of the system, the energy goes down before you move it too far from the center, and then of course it goes up. So there's a minimum in the energy in an off-center position, which is very interesting. So this is a dynamic effect because it doesn't settle in one place when it goes off-center, except in germanium. In germanium, actually, because the tendency is so strong, the lone pair wins the competition. And so the germanium goes into one side, becomes ordered, the symmetry gets lower, and you have a totally distorted structure. And the germanium systems are not as interesting from the optoelectronic point of view. So this off-centering is a key. So if you imagine an energy diagram where you have the blue atom, which is the lead 2+ or the tin 2+, in the center of the octahedron, the highest occupied molecular orbital is S2 in character. So it has lone pair character, and that's the highest occupied orbital. And by extension, the valence band, the top of the valence band has a lone pair characteristics. Now, when you start moving this away from the center, you stabilize the lone pair as it gets thermodynamically expressed. And as you stabilize the lone pair, you stabilize the top of the highest occupied state, and it comes down in energy. And so when you go off centering, and it's a dynamic process like this, and it doesn't settle. And so that causes part of the dynamics and the disorder in this material. How do we know this is happening? This is, we figured this out using pair distribution function analysis, X-ray scattering, with Ramses Sadri, and we found that in order to best fit the data, you have to move the atoms off-centering with respect to the octahedron. So the tin actually has the most displacement, and the lead has displacement less than the tin. And so another thing we found is when you heat the samples up, the displacement becomes bigger. So at higher temperatures, the displacement becomes more offsetting. And that this is also shown here in a different form. On the left, here we have a simple energy diagram, MO diagram for an octahedron, where the highest occupied state is the s orbital. That's because you do not allow this s orbital to stabilize, so you destabilize it and make it highest in energy. On the right, we have the distortion where it becomes stabilized and then it becomes low in energy. And we know, and this distortion is more as you raise the temperature. So what happens when you go off centering? This goes down. The other levels are not really affected that much. And so this HOMO-LUMO gap, which is basically the band gap in the semiconductor, becomes wider and wider and wider as you go more and more off centering. But when you heat it up at high temperature, it goes more and more off centering. So that explains why the band gap increases with rising temperature. Raman spectroscopy also confirms this. If you do a Raman spectra on these materials, at room temperature, you see a very broad Raman spectrum. And that doesn't make sense because these are crystalline structures and they should have well-defined peaks. You do see the well-defined peaks when you go down at very low temperatures, like 79 Kelvin. But at room temperature, you see nothing, very broad. And basically, it looks like a liquid. If you take a liquid and you run the Raman spectrum, this is what you're going to see. So in a way, it's like a liquid-like behavior, even though it's a crystal, and it vibrates at all frequencies. And that happens for two reasons, because of the lone pair goes off-centering, and also the KAIST cations can be moved off-centering as well. So that arrangement makes everything dynamic, and therefore, when you excite electrons across the band gap with illumination, this dynamicity causes the electrons and holes to get lost for a while before they can find each other and recombine. Because the lattice has changed. By the time they get to the excited state, the lattice has changed. And so it takes a while to recombine, and that lengthens the lifetime of the carriers, of the photoexcited carriers. And that also shows, this is on the right, we have a photoluminescence spectra for the tin case, but it applies to both of these perovskites. The tin emits at 950 nanometers, and then when you raise the temperature to 60, 90, 120, all the way to 210, the luminescence persists, which is remarkable. Most systems will quench, but it also moves to the blue, and that's consistent with a widening of the band gap of the material. So this is the consequence then of this lone pair. On the right, we have the band structure of the lead perovskite, cesium lead bromide, and on the left and on the right and middle, we have two isostructural perovskites, one with strontium instead of lead, one with cadmium instead of lead. Neither cadmium nor strontium have a lone pair, and you see how different the electronic structures are. In fact, the valence bands are very flat, meaning that the holes are very, very massive and immobile. And these materials do not have any of the properties of the lead and tin. Another thing is this anomalous band gap behavior. If you make a solid solution between the lead and the tin, you don't get the Becker's law. In a classical semiconductor, let's say if you make a solid solution between silicon and germanium, the intermediate compositions will have intermediate band gaps following more or less a linear behavior. The same if you mix cadmium selenide and cadmium telluride. But here we have an anomalous trend where the middle compositions have even lower band gap than the lowest band gap member. So the lowest is 1.2 eV, but you can get down to almost 1.1 in the middle. And that is very exciting because that means, as we demonstrated in 2014, you can extend the solar absorption spectrum well into the near infrared and therefore collect more light. And this now has become the basis for fabricating tandem solar cells, perovskite tandems, where the bottom solar cell is the lower band gap perovskite, and it's always a mixed lead-tin perovskite. And these tandems now have reached very high efficiencies, closer to 27% or so. And so that's based on this discovery. So the take-home message is the lone pair of tin and lead in halide perovskites underpins all the unusual and remarkable properties, I think. This is something very simple, any chemist can appreciate, but most people actually still, I think, don't quite appreciate this effect. Now, chemistry, of course, can be changed, and you can do synthesis of derivatives. If you add an additional organic cation that is too big for the cage, and you mix now, you have two cations, something that does fit and something that doesn't fit, you can actually make a series of two-dimensional perovskites. And these have a slab that is a perovskite, and then the slab is separated by cations, the long cations, which act as spacers. And so if you control the synthesis, you can make many members, anywhere from, in this series, n equal 1, which is only one layer of perovskite, to n equal 2, you get 2, and then 3 gets thicker and thicker, and then all the way to 7. And so in a way, some people call these quantum wells because of alternating band gaps between the perovskite and the spacer. And this, of course, the properties approach that of the 3D. And in the middle, we also discovered a hollow version, which is not quite 3D because it's hollow, but not quite 2D. So those are interesting as well. So here's 4 different kinds of 2D perovskites. The first kind is called Rudolphson Popper. And here we have perovskites, and then between we have organics. And why do they call this Rudolphson Popper? This name is borrowed from the oxide literature that is much older. And you see here an oxide perovskite in yellow, and you see this layer is shifted over this layer by 1/2 a unit cell. And the same happens in the other direction, 90 degrees. And this stacking defines the Rudolphson Popper motif, because there's this stacking down below here, where you see in the oxide, they're not shifted. They're directly one on top of the other with this cation. And this stacking defines them as Dion-Jacobson. And so we made perovskites where actually they have this stacking as well. So these are the DJ perovskites. We have also seen perovskites where, with very small cations, where we have one cation in the cage, and then the small cations alternate order between the cages. And the interest here is in stacking, in one direction, you see the stacking is shifted by 1/2, just like Rudolphson Popper. But if you turn it 90 degrees and look at it again, the stacking is eclipsed, not shifted. That's more like Jacobson-Dion. So that's an interesting one here as well. And then we also have this one that has dications across. So now you expand the chemistry horizons really to a big degree, because now you can start experimenting with everything here. So you can have the same spacer, and you can start making the layers thicker and in one study, or you can have the same thickness and change the spacer. And we did extensive studies on this and stabilities, and we found that these are much more stable than the 3D perovskites. And so here is the structures that we solved all the way to n=7. So these are crystal structures that are required to understand these at a fundamental level. And also the coordinates that are being generated are used throughout the world by theory groups who need the coordinates to do the proper modeling. They don't have to guess what the structure is. And all the way to 7, you can see here, for example, the photoluminescence spectra in the low right. You see the maxima are very regular, and everything is where it's supposed to be. So as the band gap gets smaller, the PL moves to the red, and the same for the absorption. So these are some review articles that we have written in the past 2 or 3 years in various aspects, especially this chemical reviews, which combines everything, all the systematic understanding that we have at this time. And so it's a good reading for whoever is interested. Now, what can you do with the 2D perovskites? Because you might think, well, they're not going to be as good as the 3Ds. First of all, one thing that came out right away is that much more stable than the 3Ds. So that's interesting. They're soluble, so you can make thin films and cast them. And this is the first result we got in this diffraction pattern, where we noticed 2 things. First of all, the film did not have all the diffractions, did not have all the Bragg peaks. This black diffraction pattern is the calculated pattern. These are all the peaks that should be there. The film, when made, only has few reflections. And the reason for that is it was very strong orientation. This is a butyl ammonium. Very strong orientation where the layers are perpendicular to the substrate. And the second remarkable finding was that after months, even a year, it didn't change. And that's remarkable because if this was a 3D film, it would have decomposed. And one of the reasons is the stability is that these are more hydrophobic because they have these long chains. So the contact angle here is higher, for example, than here, which is the 3D material. So, okay, that makes sense. But also, the ion migration is slowed down significantly, maybe by orders of magnitude, in the 2D compared to the 3D. And that also contributes to the stability. But this was a pleasant surprise, the very strong orientation, because if you want to make a device like a solar cell that requires electrons and holes to move up and down, perpendicular to the device, you want this orientation. You don't want this horizontal orientation where it's a blocking direction, so because of the organics. And we studied this by grazing incident wide angle X-rays. And these things, in fact, they diffract like single crystals, although they're not single crystals. So they have this discrete spots rather than the rings here. So that was really a pleasant surprise because that allows you to make a functioning device. And that's what we were worried about with the 2Ds in the first place. So we got together with Aditya Mohidar at Rice University and demonstrated that very stable solar cells could be made with 12% efficiency, which at the time was a very remarkable result because the efficiency of the 3Ds was close to 16–17% in 2016. And although this was not as good, it was definitely over 11% with no hysteresis. And this plot here caught the attention of the community in the lower right. And this is the stability plot. Monitor the device stability, which indicated that compared to a 3D perovskite solar cell, this was orders of magnitude more stable, thousands of hours. And that excited a lot of people, and they really, a lot of them became believers, and the 2D actually was going to be an important perovskite. So then people started combining 2D and 3D in the same device, in the same film, making mixtures. And they showed that the devices actually combined, instead of becoming worse, they combined both good things, the high efficiency of the 3D and the high stability of the 2D. This is remarkable. And not only that, it also made the 2D proximity to a 3D grain, made the 3D a better semiconductor, as shown here in this lifetime of the photoluminescence of the 3D. When there is zero 2D in there, we have one decay, a faster decay, but when you have some 2D next to it, we have a longer decay. So there's some passivation also possible in the 3D perovskites. So that is now, a lot of the papers have, most of the papers have this 2D, 3D mixture in the device. These are the Jacobson-Dion, and this is another very interesting family. It's not exactly the same as the other, the Rudess and Popper. Here, to get Jacobson-Dion, you need a short spacer, like these spacers here, relatively short, and you need dications. And when that happens, you get this, in between the layers, you get this case. And that forces the iodine here and the iodine here across the layers to talk to each other. They touch each other, and they in fact interact positively to change the properties of the perovskite. That's why for the same thickness, these perovskites have lower band gaps than the Rudolph-Popper band gaps. So then we compared Rudolph-Popper, Jacobson-Dion, and alternating cation, and found a very interesting effect, and that was published in this paper. We illuminated these three different materials, and so here you see the three different structures. Down below, this is Rudolph-Popper, and you see it's shifted by half. Here we have alternating cation, which is, you see, not shifted here, but shifted in the other direction. And here is Jacobson-Dion, not shifted in both directions. And this is 4.12 is the iodine-iodine distance across the layers. This is a little bit longer, 4.46 in the alternating cation, and very long, 7 angstroms here. So in the RP, the layers really don't talk to each other. In the Jacobson-Dion, they talk to each other because the band gap becomes shorter, smaller, and in this one, it's in between. Upon illumination, you see a remarkable result where there's a contraction in the, indicated by the diffraction pattern. In fact, it gets contracted, and the most contraction in the lattice parameter, especially in the stacking direction, happens in the Jacobson-Dion, which is shown here, out of plane contraction. And however, this one, the Rudolph-Popper, which has very long distances and the layers really don't communicate, nothing happens. No contraction, no expansion, or anything else. And there's some contraction in this one here. So that was surprising. Why was that happening? We also noticed that the mobility and the charge transport in the stacking direction were becoming better. For example, here in this conductivity, if you monitor conductivity versus time, you see after some time of illumination, conductivity becomes almost double. And as a result, the mobility also doubles. So what is going on here? And the way to explain this is, as these iodines are very close together, when you excite, we excite across the band gap, you create a hole, which is located in the iodine sublattice, especially the terminal one. And then the electron goes into the conduction band, which is based on the lead. The hole, because these are so close, it kind of like partially oxidizes the terminal iodide and makes it shorter. And kind of like parts of the holes localize here. And it's like making an oxidative coupling, trying to make an iodine bond across the layers, and that contracts the lattice along the stacking direction. At the same time, as shown by the calculations, now you have some path for holes to cross from one layer to the next, as the valence band becomes a little bit broader. And that can account for the higher mobility. And the devices then, also after some illumination, suddenly after 10 minutes of illumination, they jump in efficiency from something like 16% to 18%, which is quite interesting. These are the hollow perovskites. If you use ethylene diammonium, you don't make a 2D perovskite. You make something that is 3D, and it has the same diffraction pattern as the 3D. So it almost looks like it doesn't work. If you use ethylene diammonium in the synthesis, you get these diffraction patterns, which look just like the 3D. And you say, wow, it didn't work. However, if you look at the band gaps, the materials actually have different band gaps. And the more ethylene diammonium you use in the synthesis, the wider the band gap. If you look closely, there is some shifting in the diffraction pattern. And so also the wider band gap with more ethylene diammonium is indicated by the blue shifting of the photoluminescence. So that was a surprise. We measured the density of the crystals, and it looks like it's lower. The crystals have lower density than the starting 3D material. And this happens both for tin and for lead. In fact, you can make a lead, methylammonium lead iodide hollow perovskite that has a band gap of 2 eV rather than 1.55. And so that indicated, and we verified with X-ray crystallographic refinement, that there are vacancies, lead vacancies, and iodine vacancies, and that explains the low density. It explains the wider band gap because it's not really as three-dimensional as before. And the presence of ethylene diammonium was verified by dissolving the crystals in DMSO and doing NMR spectroscopy and seeing that they are there. These materials are far more stable than the corresponding 3D materials because as we did this collaboration work with Saiful Islam, now at Oxford University, and Joachim Meyer at the Max Planck Institute in Stuttgart, we realized that these are far more stable, and the reason they are more stable is because the ion migration is frustrated inside. So in other words, the ethylene diammonium, cation, and the vacancies frustrate the ion migration and raise the bar, raise the activation energy to slow them down. So this is quite interesting. And we were able to make stable tin-based solar cells that were actually at the time record breakers, about 7%. So back to the 2D perovskites. So these are, as I said, are quite interesting materials. They're flexible. You can make different organics, and you can actually tune the properties by intercalate them in between the layers. And again, almost every group, this is not our work. This was done by Professor Xiaojing Wu at Xi'an in collaboration with us. Every group is reporting far better stability when the 2D, 3D system is combined and gives you a solar cell. So let me skip over to this work, which is the latest work. And here, it is a work with Didier Mohit. It was just appeared a month ago. And we did systematic work for a long time. People wanted to make multiple layers of 3D and 2D. For example, like shown here, to have one 3D, and instead of mixing 2D and 3D, put the 2D on top of it to make that kind of a device. And it wasn't possible because the solvents people were using for the 2D casting over 3D were destroying the 3D layer underneath. So we did a systematic investigation of solvents and found that in this, as you see here in this upper left, that there are two properties that determine the solubility of 2D perovskites in these solvents. One is the donor number. This is basically a coordination number, ability to coordinate as a Lewis base, shown here, and then the dielectric constant of the solvent. And here we categorize them in these regions. So below the dielectric constant of 30, all these solvents, ether, butanol, isopropyl alcohol, ethanol, acetone, and so on, they can coordinate to lead, for example, but they don't have enough dielectric constant, so they don't dissolve the 2D. Toluene and so on, these are low anyway, so they don't dissolve. Over here, you have high dielectric constant, but low donor number. You also don't dissolve through D or 3D. And if you have a little bit higher donor number and high dielectric constant, like acetonitrile, propylene carbonate, and so on, you can dissolve the 2D, but not the 3D. And if you have very high donor number and high dielectric constant like DMSO, DMF, NMP, GBL, you can dissolve both. So that's no good. This is a sweet spot where you can dissolve one and not the other. So this allowed us to deposit a 3D film, and then on top of it, deposit a 2D without destroying the 3D. And so this kind of like is a breakthrough because now we can have hetero-layered devices, and these devices are quite stable. Here's a stability plot again of a device that has 24% efficiency, which is a 2D on top, 3D on the bottom. It's very stable compared to other devices that have mixtures of 2D and 3D. And so we characterize these things, and we can do different thicknesses and different N values on top of it, and the diffraction patterns are shown here. And we can characterize them. For example, you can take absorption spectra, and you can see the absorption of the 3D, and then superimpose the exciton absorptions and so on of the 2D. So here's one film. You see it has N equal 3 on top of 3D. This is N equal 2 on top of 3D, N equal 1, and so on. And so this we characterize them thoroughly. This is TOF SIMS data of the stack. It shows us first, on top you have the butyl ammonium that comes out. This is a 2D, and then after you exhaust that, you hit the 3D. And so these are well defined and well characterized, as you see here in the left cross-sectional images. So these are the work functions of the various materials, 3D and various 2Ds. And based on these, N equal 3 and N equal 4 have appropriate valence band energies to act as good Hall transport layers for this 3D absorber. And so we were able to make both NIP devices and PIN devices, and show that the NIP devices are higher performing, they're better behaving, where this you see efficiency of a device as a function of 2D thickness on top of the 3D, and the sweet spot here is between 30 and 60 nanometers. And here's the examples of the device characteristics. And of course, this is the same stability plot that is very exciting, because these things are even more stable than the ones that have just 3D, 2D mixtures. So this is a very active area. Again, to summarize, it's a long history that goes back a number of years. Didn't have time to say the whole story here, but it goes back to the 50s, 78, the report on the methylammonium lead iodide, the Gretzel cell in 1991, Tamotsu Miyasaka's nanoparticle liquid solar cell in 2008, 9, our paper, and all the other papers. And so now we're pushing 30% on some tandem perovskites, and the stability problem is also increasingly being handled and treated. So with this, I would like to thank you for this great invitation to tell you about that, the story, and I will be happy to answer any questions.
Okay, so thank you very much for your impressive presentation. Then we have the 3 questions, but we will take the 2 questions. So let me read the question, and you can answer to the audience. Okay. The first question: in the 2D 3D mixture, can you control the ratio of 2D and 3D perovskite freely?
Yes, we can. In the mixture, not the hetero layer, I assume the mixture. Yes, you can control the mixture, and so there's an optimum ratio that you have to find for the best performance.
Okay. Then the second question: are there any disadvantage and the limitation of the particularly stacking the 2D perovskite thin film? And the
The one limitation is that if you have a pure device based on 2D only and not 3D, that you can have very high efficiency, but it's never going to be as high as 3D. So that's because, you know, one dimension is still not quite functioning as well as the other two. But when you have this combination, then you solve the performance problem. Another challenge, but again, it's progress is being made, is to cast 2D films of a particular N value, particular thickness, without getting a mixture of other thicknesses as well. And that's another challenge.
Okay, so thank you very much for your kind explanation and wonderful presentation. Let's thank the professor. Okay, thank you.
You're welcome.